Fluidic actuation has proven to be the most popular approach to controlling soft robots due to the commercial availability of control components, ease of power delivery, and existence of lightweight actuators. However, a significant challenge in pneumatic actuation is the scalability of fluidic control components. As shown here, the sophistication and complexity of many soft robots critically rely on simultaneous and independent control of multiple actuators. Usually, the control of large array of actuators requires each actuator to be connected to a dedicated electromechanical valve for independent operation. This places a practical challenge in designing soft robots with many actuators. Independent control of large array of fluidically driven actuators, particularly for applications in shape display and haptics, is cumbersome and complex due to its reliance of external valves and electronic control systems, as seen in these figures. Challenges with approaches like fluidic demultiplexing are that they are only able to control one actuator at a time, thus increasing the refresh interval proportionally with number of actuators. In this work, we present a fundamentally different approach to independent control of actuators that bridges the trade-off between direct actuation and fluidic demultiplexing. Our approach is inspired from the dot matrix displays that, as shown here, that are capable of controlling a large array of outputs, which are LEDs, with a refresh rate that's higher than a 7-segment display and have a good scalability. As you can see here, in the dot matrix display that we have shown, although the display shows letters U, C, S, D, only one row of LEDs is on at any given time. Sequentially addressing each row of LEDs enables display of a particular image with reliance on persistence of vision to maintain the perceived image. We take inspiration from this approach on how a dot matrix display works by controlling the flow of electricity through each row and column pair for our approach. We call our approach fluidic matrix circuits. To enable fluidic matrix circuits, we construct an intermediate circuit element equivalent to an LED. We call it Fluidic Logic Module. The Fluidic Logic Module generates a pressure or a vacuum signal based on the state of the mass flow through its inlet or outlet. When the mass flow through its inlet and outlet is enabled, it generates vacuum at the signal line, thus retracting the cylinder. When the mass flow at the outlet is blocked, it generates pressure at the signal line, thus actuating the cylinder. Thus, when these fluidic logic modules are arranged in a 2D matrix with all its outlets connected together along the column and all the inlets to the fluidic logic module connected together along the row, we get a fluidic matrix circuit that is capable of addressing multiple independent actuators using limited number of solenoid valves. In this case, we are able to address 9 actuators using 6 solenoid valves. The array of actuators connected to the fluidic matrix circuit is refreshed by sequentially addressing each row within the matrix for a short period of time. As shown over here, depending on the state of the inlet solenoid valves and the outlet solenoid valves, enables us to independently control each actuator connected to the fluidic logic module. We demonstrate the implementation of the fluidic matrix circuit for controlling a fluidically driven shape-changing display with 25 independent actuators. We control these 25 independent actuators using just 10 solenoid valves, 5 on the outlet and 5 on the inlet of the fluidic matrix circuits. The shape-changing display could render various shape patterns, including a variety of geometric shapes, numbers, graphics, incoming visual data, and many other plots. In addition, we demonstrate the shape-changing display rendering every frame of a snake game as the position of the snake was dynamically updated on the 5x8 grid. The two-dimensional array of actuators was refreshed by sequentially addressing each individual row within the matrix for a short period of time. We demonstrate the use of 5x5 shape display controlled by a fluidic matrix circuit to generate desired patterns to convey and manipulate objects. Here, the tactors were used to generate height profiles to confine the object within a cage. The object is then guided alongside the desired path using actuation from the tactors. We demonstrate the pattern generation for object manipulation to convey a ball along the row, column, and diagonal of the shape changing display. We also demonstrate the implementation of the fluidic matrix circuit for controlling a haptic vest consisting of inflatable airbags. These airbags provide a force feedback to the user when bag is inflated. The fluidic logic module generates a pressure signal by addressing the corresponding row and column in the fluidic matrix circuit. This pressure signal is used to inflate the pouch. Then by addressing the same row and column connected to the pouch along the fluidic matrix circuit, the pouch is rapidly deflated to give a sensation of being hit by the soft object. The deflation of the pouch is accelerated by generating vacuum using the fluidic logic module corresponding to the pouch, rather than only relying on the elastic restoration force. Here we control 16 independent pouches using just 8 solenoid valves. This work presents a novel fluidic control technique called fluidic matrix circuit that addresses the challenge of controlling large array of individually addressable actuators using limited number of solenoid valves